let me go to the writing screen now. So this is the screen where I write, and I will now talk about quantifier. It is also a topic in the propositional logic chapter. Okay, this is also a topic in the propositional logic chapter. It is called quantifier. Quantifier. Okay. Well, so what is that? Quantifier actually, it is about quantity, yes. So there are two types of quantifier. We call this existential quantifier, and another one is universal quantifier. So there are two types of quantifier. Let me tell you what is quantifier. So it is about quantity when we state something. That means say I'm writing any statement, any proposition. So say today is Monday. This is a very simple example. Okay, today is Monday. So if it is one proposition, then you can think of a number. I mean, when it is true, when it is correct. Is it correct for every day, or is it correct for someday? Okay, so that is the idea. So you can think of every day or someday. Let me give you another example, another statement. I'm writing if you study regularly or study hard, okay, you will pass. Then you pass. Okay, then you pass. So if this is the statement, this whole thing is a proposition, right? So is it true for everybody? Is it true for some person? So
Sir, it's true for everybody.
so you can think, okay, so you can think two situation, that is about the quantity, and two situation like maybe everyone. So universal is that situation, that is everyone, every day, every number, okay, everything. And existential means it is not correct for everybody, or maybe not every day, maybe not every number, but someday it is correct. So you can say, okay, sir, the first one is correct for some days. That is, some days are really Monday and some others are not. So you can think this may be existential quantifier related to this thing. And the next thing is, okay, you are saying everybody can be included here. So it is one example of universal quantifier thing. So in these two sentences or statements, there is no quantifier included, just a sentence, nothing included here. So if I write something, then the quantifier will appear. You will understand, oh, okay, this is the quantifier added with that. Say, let me give you another example. Say, I am saying, I'm saying another example, 2 divides x. Okay, so that means x is a number, and I am saying 2 divides x. So what is divides? That means x is divisible by x. That means x is even numbers. So is it true for all the x numbers? No, it is not.
No, sir, only even.
So only even numbers. So you can say, okay, that is existential quantifier, and you can say, okay, there exist, I can write, okay, something like there exists, oh sorry, x, there exists like this, there exists some numbers, some x in the real number. That means there exists some real numbers in the world that can be uh, written like 2 divides x. So it is not for every number in the world, not for every number, but there are some numbers. So you write the sentence 2 divides x. This is your sentence, but there is a quantifier involved with this, because this sentence is not always correct. Sometimes it is correct, and we are writing there exists some x in the real number, so that 2 divides x. We use the symbol like this. This symbol is there exists. So you can write like this, x belongs to R, comma, 2 divides x. So we use the existential quantifier symbol like this, that is opposite of E. This is the existential quantifier symbol. Okay, so I can also write like, okay, there exists someday, okay, there exists some days, okay, so that some days, so that today is Monday is correct. Today is Monday is the statement. It will be correct for some days in the world. So this is the sense of existential quantifier. And the universal quantifier, let me give you another example with numbers. Say I'm writing x square is greater, yes, greater or greater than, I should write then, greater than or equal to x. So what do you think? Is it correct?
Yes,
Is,
sir.
is it correct for every number?
No, sir.
Yes,
Good.
sir. Where is
So why not? Then the existential quantifier should come.
Yes, sir, it's correct for everyone.
So
Because of
yes,
someone
sir,
said,
it's correct. Sir,
someone said,
it's universal.
because of yes, sir. Because of it's the
Yes, sir. Yes, sir. It was my mistake, sir.
x is the like 10, then 10 square is bigger
Sir,
than x.
we,
So 10.
if we think x equal point 0.01, then x square equal point.
X belongs
hmm,
to R.
It's not correct, sir. When we consider x equal to point something, in that time
Point.
x square will be 1 divided by that bigger number. So the value will
right,
be less
right.
than, yes.
Right, very good, very good. So that what I actually want. So you are saying the correct thing. This is, if you think about any number, then this is not universal. If you think about any number, it is not universal. It is correct. You are right. Because of what? Because point one, someone was saying, okay, say I'm writing in red color. If you think about point one is your x, so that square will be 0.01, and it is not greater, actually it is not bigger, actually it is a smaller, it is it is it is smaller than the original x. Okay, so x square is smaller than the original x. So it is happening for the smaller number, that is less than one number. Okay, but I'm trying to give you one example which is universal. So for this case, I will consider, okay, I will consider for all, I will write, okay, for all natural numbers. Then what will happen? If I write only the natural numbers, what are the natural numbers?
So whole number 0, 1, 2, 3.
Exactly.
0
Then I will, yeah, then I will not take 0.1, right? So if I write all natural numbers, then it is universal. Yes, it is universal now, because I'm not taking 0.1. 0.1 is not natural number. Natural number is 0, 1, 2, 3, 4, 5, and -1, -2, -3, -5, like that. So you use the symbol, the for all symbol. The universal quantifier symbol is this. This is for all. For all, you can write x belongs to n. Now I will write n. Then comma, then x square is greater than or equal to x. So why did I say equal to? Because of 0.
Yes,
Because of
sir.
0. Because 0 square is equal to 0. So it is not greater.
1 square is also equal to 1.
Yes, 1 square is also equal to 1. So it is not greater than 1. So I have to write equal. So greater than or equal to, it is correct for all numbers if the number is natural number. So you can use the universal quantifier, and the symbol is this. Symbol is this. So these are the two examples of quantifier. That's it. Is that okay? Do you have the concept now?
Yes,
Sir,
sir.
Yes.
can you repeat the first one?
Sir,
Yes.
sir, universal quantifier, repeat please again, sir. So for all natural numbers here, I don't understand, sir. Universal quantifier.
Yes, I understand what is your question. The thing is, if you consider all the whole numbers, not 0.1, 0.2, these are not the natural numbers. Okay, natural number means not point, only full number, only whole number. So if you consider n means the set of natural numbers. In that case, you can write universal, because all natural numbers will be applicable for this sentence. So if everything is applicable, every number is applicable, then it is universal. So about this sentence, if you study hard, then you pass. So do you think, is it applicable for every person?
No, sir.
No, sir.
Okay. Okay. So if it is
Because
not,
some people are pass and some people are fail.
okay. So if you study hard, you will pass. If you think that this is not correct for every person, then it is not universal quantifier. Okay, again, some person may be available in the country so that this sentence will be true. That is again existential quantifier. But if it is correct for everybody, okay, someone was saying in the beginning, if you correct for everybody, say I'm thinking, okay, yeah, it is correct for everyone. If you study, then you will write, okay, for all persons. And if you write, no, sir, all persons, it is not correct. Then write it like this, all sincere persons. Is that okay? Then
Yes,
you
sir.
can say, okay, you can say, yeah, now it is okay, sir. If the person is sincere, then fine. If you study hard, then you pass. This sentence is correct. So in this case, this is the example of universal quantifier. because we are talking about all the sincere persons, all possible sincere persons, and if it is possible for all, that is the universal quantifier. Okay, so this is the concept.
স্যার এক্সিস্টেন্সিয়ালটা হ্যাঁ এক্সিস্টেন্সিয়ালটা একটু আবার বুঝাবেন?
Okay, existential means something may be correct, but it is not correct for every situation, all situation. Maybe it is correct only for some. Say, for example, I am saying about this x square is greater than or equal to x. Say this thing again, okay? Or I'm writing x square is greater than x. So what do you think? Is it correct for every number?
No, sir.
Then it is the existential quantifier example. You will write, okay, there may be some numbers, there exists some number in the set of real numbers, and this statement will be correct. So this is the existential quantifier. Say I'm writing, okay, say I'm writing there exists some number in the natural number also, there may be some number in the natural number also. X is a prime number. So what do you say? All numbers in the natural number is prime number? No.
No, sir.
This is only some of the numbers. So how many? 2, 3, 5 or 17 or 100 does not matter. If not every one, you will think existential. That's it. Okay. What about this? What about this? If I write sum of three angles, sum of three angles is 180 degree. So is it correct for all triangles or is it correct for some?
Oh, sir.
Something for all?
That is sometimes.
Oh, sir.
For all triangles. So you will write, okay, for all triangles. So this is the universal quantifier. You will write for all triangles, comma, this. Okay. So that is the concept about quantifier. Done or any more question?
No, sir, complete.
Okay, good. So now you need to practice at home about the sentences and expressions. Okay, I can give you like A and not B, okay, and then XOR, then C, then something E for like this, A implies C, okay, blah blah blah, this type of. So you will write the sentences. Or I can give you the sentence and you will write the expressions. So this thing you practice at home. And the truth table you practice at home. Another thing, the truth table. How? I will give you one expression. Say for example, one expression is, okay, A implies B and then XOR C. This is one expression, and I am also giving another expression, something, and I will say, okay, this is one expression and that is another expression, and prove that they are same, prove that they are equal. So prove the expressions are equivalent. I will write equivalent. Okay. So actually you are proving that they are equal, but in question I will write prove that equivalent. So how you will prove that? You will make the truth table. You will make the truth table. So in the truth table you will write the variables first. So mostly I will give the three variables. So if you have three variables, then how many lines will be here? There will be how many lines?
8 lines, sir.
8 lines. So there will be eight rows for three variable, right? So 8 rows you will write with T and F. So you continue with left part. Okay, you will make the necessary columns, and then you will write the one expression that may be x. So you will find out the x expression, and then you will find out other things, okay, from the right side, and then you will also find out the column for y, that is the second expression. So when you can find out the expression for x and expression for y, you will see, yeah, they are actually same thing. Yeah, they are actually same thing. Okay, but in this line you will not write that they are equivalent. If you write, then I will give you marks. Okay, because if this is true, then this is also true. If this is false, then this is second one also false, like that. If everyone is exactly same, then they will be equivalent. But I want you to write another column that will be x double implication y. So if you write another column x double implication y, you will see every time it will be true, 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 right? So all things will be true. All 8 results will be true. So if it is all true, then you can say, yes, this is all true. So it is called tautology, right? So when x double implication y will be tautology, you can say x and y, they are the equivalent expressions. So this way you will prove the given question. Okay. So tautology means the expression which is always true. Another thing is there. Let me just tell you the name. Maybe some other time we will talk about that. Okay, some other time, like after the first term exam. Okay, in the midterm syllabus we will again do something, and then I will discuss again about this. It is called fallacy. It's called fallacy. So what is the fallacy? Fallacy is the opposite of tautology. It is like the expression, logical expression which is always false, which is always false. Okay, that is the fallacy. That is called fallacy. You understand now? So tautology is one term which is always true. Fallacy is another term which is always false. We are not talking about fallacy right now. We are talking about tautology. That means x double implication y will be tautology. So x and y separately equivalent. Okay, x I already written that thing. Okay, xy is a tautology. So x and, let me write capital X and y are two equivalent expressions. So you will answer like this. Is that okay? Do you understand what I say? So that will be the truth table, and that will be the process. You prove two expressions are uh, equivalent. Is it okay?
Yes, sir. Okay.
Yes, sir.
So that is the summary of this chapter, and let me start another topic, another chapter. This is very small, and I will show some of the examples tomorrow. Then this chapter will be finished, and then I will start the encryption decryption, and that is the last thing in the first term syllabus. So about encryption decryption, I was talking to I mean watching the movie will be better. It will be interesting to you, so before that you watch. Today and tomorrow I will finish the new chapter, the second one. What I am starting now, it is called algorithm. That's it. You already know algorithm, so I do not need to explain that much on this, isn't it? What do you think? So tell me, what is algorithm?
Sir, algorithm is the steps for solving a problem.
Okay, good. It is correct. And anything else? If you want to add anything else on
Sir,
the idea.
it's a set of rules actually, which we have to follow.
Okay, there are set
Sir,
of rules. Yes.
we can solve problem if we follow its algorithm. Mainly, sir, why how we solve our problem? It is set of solved format, sir.
Okay. Yes, correct. And
Mainly, sir, it is a procedure for solving a problem, sir.
okay, process or procedure. Yes, that is also correct.
And sir, it's a finite sequence. I mean, sir, when we'll develop some algorithm, there will be some fixed steps.
Yes, that is another important point. There should be finite number of steps. There should be limited number of steps. Maybe 100 steps or 500 steps, but it has to be limited. Okay. You cannot just use unlimited loop and then you will expect the result will come. No, there should be finite number of steps. Okay, so you can say a set of finite number of steps to set of, okay, a procedure. Let me write procedure. A procedure of finite number of steps to solve a specific problem. So this is the definition of algorithm. You can write in your own words, no problem. But main point is it is a process or procedure, and I can also write pre-planned. Okay, that is you will make the plan previously so that or well planned or organized plan procedure, like that you can use some word. So finite number of steps, this is important thing, and step by step, that is also important thing. Okay, you can also write, okay, a finite number of serial steps, that is steps in order. Or I can write serial. Serial means what should be done first and what should be done second, and then what is third, and then what is fourth, like that. There should be a seriality, that is consequence, and there should be a specific goal. You have to do something, that is there should be some target, so that you can solve the problem, and that will be called algorithm. So it is basically the previous phase of writing the computer program. Okay, previous phase of writing the computer program. So before writing the programming code, we usually plan how to write the program or what to do with that program. So that will be the algorithm. That is the planning. And another word is also there, which is called flowchart. So what is flowchart? Flowchart is actually the same thing like algorithm, but it is the step-by-step procedure with symbol, right? So flowchart is the same thing by concept. What you understand by algorithm, flowchart is exactly same thing, but we use the steps by symbols or diagrams. Okay, is that okay?
Yes, sir. Okay.
Steps in the algorithm, steps in the algorithm presented by diagrams. Okay, that's it. So this is flowchart. So there is nothing new to understand. You already know all this. You have done. So this is our next topic. And in this, actually, I will show you some of the example algorithms for simple mathematical things. And I will also give some questions in the exam so that you can write the algorithm for those simple mathematical calculations. Only simple mathematical calculations. Say, for example, finding the average of numbers. Okay. Say, for example, finding the uh, uh, what area of a triangle or of a circle, or finding the LCM. LCM means in Bengali it is called Losagu, right? LCM or GCD. GCD means Gosagu of two numbers, right? Say finding the largest number, say finding the smallest number, uh, say finding the sum of 100 serial numbers. This type of thing already you know, because in other courses in computer science courses you have done all those algorithms and also computer programs. So all these will not be complicated at all. It will be very easy, but it is included in our syllabus, so I will do that, and I will show you some of the examples and you will do practice at home. So I will show some examples here in the class, and maybe in the exam I will give another question, not exactly the same question, but the process is same. So if I do finding the largest number, so in the exam maybe I will give, okay, find the smallest number, something like that. Not exactly same question, but similar question. So if you practice at home, it will be easy to answer. Okay. Say, uh, now let me tell you another thing. You need to understand the structures in coding or in algorithm. So sometimes we use the decision structure, right? What is the decision structure?
Sir, decision structure is the structure where we decision any kind of decision. If we like kind of if else, it's a one kind of decision structure and
Exactly.
looking structure in programming. We saw that there are three type of loops. One is for loop, another is do while loop, and another is
Yes. You are right. So sometimes we use if, then something then. Okay, so that is called the decision structure. And sometimes we also use if and then else if then. Okay, that is another type of. Okay, let me write number 2 here, or I can write number 2 below. Okay, so like that. So these are the decision structures. And about looping structure, there are different structures. You can write do, then something, okay, then what, end do, isn't it? Say while, then something, then end.
for
Or you can write for, okay, yes. So for, then something, then what, next. Normally these are the common structures.
yes and
So
next.
okay, so these are the structures you may need to use inside the algorithm also, and for coding also. So there are other things like input statement and output statement, right? And start and stop. What is start and stop? What is start? What is stop? Who can say what is start in the algorithm? What does that mean?
Sir, it's a beginning point of any function, and stop is similar kind of break operation. If we want to break a statement, then we use stop.
So what is the meaning? What is the meaning of this? What you can understand by that?
Sir, for any loop, the initial point and the ending point.
Yes.
Because in a loop, we start from 1 go up to 100. So 1 is
So
start and 100 is stop.
so is it necessary, or you can give or you cannot,
So
or
if
is
we
it
don't give a
mandatory?
start stop, then we have to give a start. Like,
Okay.
we can also do it without start stop, but then it will continue for infinite.
Okay. So anyone has any other idea? Different idea?
Sir, is it not necessary to put it in program start and stop? But in our simplicity, if we start and if we imply the start and stop, then the program cannot repeat continuously step. It can be it can be run a one time or the looping time. But if we don't use start and stop, then loop will be continuously um, uh, output the next procedure.
Okay. So okay, no problem. I do not have enough time. Let me just finish this quickly. So start is very important in algorithm. Start is actually written in the algorithm for preparing the situation before writing your code. Say for example, you in C programming, you include the header files, right? So what what operations or what actions you will use in your computer coding or in your program, the header file will be dependent on that. Okay, so if you need some specific actions or activities, you need specific header files. So this is the meaning of start. Start means you prepare the situation. Environment preparation is actually the start in the algorithm. You understand now? So this is mandatory. It is essential. So what are the things we are writing in the include file? This is not written in the algorithm, but start in the algorithm means you prepare the environment, and stop means you close the program and go back to the original environment. So these two are important in algorithm. Input statements are giving some input to the computer. Sometimes you can write scanf, okay, read and blah blah blah, many other different codes. That is not the main point. Coding word is not important in algorithm. We can use input in the algorithm, and we can use output in the algorithm. Output, or you can write print or display or printf. Okay, there are many different ways you can write. So in the algorithm, it is not coding, but it is the idea what you are doing. So idea of output is you are getting the output result. So about decision is what? You are taking a decision. That means if this, then do this. If not, then do another thing. So that is the decision. And looping structure means the same action. What is the looping structure? Same action will be repeated. So if you think about do and while, it is the conditional loop. It is the conditional. That means based on the condition, repetition will be done. Based on the condition, how many times it is not fixed. How many times it is not fixed. It is based on the condition. And the last one, for, it is not conditional. It is fixed time. It is fixed time of iteration. That is, repetition will be fixed. Okay, so fixed number of iteration. So that is the idea. And let us finish the class here and come back again tomorrow. I will show you some of the algorithm examples.